Okay, you know the feeling. It's one of those dry days, you're walking across a carpet, you reach for a metal doorknob, and zap! You get that tiny, unexpected shock that makes you jump. It happens to all of us, right? It almost feels like some kind of weird, random magic, or, just a really minor inconvenience. Well, it's not magic at all. It's pure physics. And today, we're going to solve this little everyday mystery. We're going to pull back the curtain on that invisible force behind the spark and see exactly how it all works.
To get our answer, we have to go small. I mean, way, way down into the invisible world of atoms. Because the secret behind that static shock, it's hiding in the fundamental building blocks of, well, everything.
So it all boils down to this thing called electric charge. Now, this isn't some weird, exotic concept. It's a property of matter that's just as fundamental as mass. And it always comes in two flavors. You've got positive and you've got negative. Inside every atom, we've got our main players. Smack in the middle are the positive protons. And they're locked down tight in the core, the nucleus. But zipping around that nucleus are the negative electrons. They're super tiny, they're restless, and this is the most important part, they are free to move. Their ability to just get up and go, that's the key to this whole thing. And here is the biggest rule of this entire game. You can't just make charge appear out of nowhere, and you can't destroy it. You can only move it from one place to another. Think of it like a deck of cards. You can shuffle them, you can deal them out to different players, but the total number of cards in the deck never, ever changes. Okay, so if charge just gets moved around, how does that actually happen? Well, it turns out there are three main ways we can get those little electrons on the move and create the imbalance that we call static electricity. First up, the most common method, charging by rubbing. You absolutely know this one. It's when you rub a balloon on your hair. That friction, that rubbing motion, is literally scraping electrons off of your hair and piling them onto the surface of the balloon. So now your hair is positive because it lost electrons, and the balloon is negative because it gained a whole bunch of them.
The second method is even more straightforward. It's charging by direct contact. So imagine you've got that negatively charged balloon. If you just touch it to something neutral, some of those extra electrons are just going to flow right over, trying to find more space. It's really just like pouring water from a totally full glass into an empty one until the water level is even between them.
Now, method number 3. This one is the most subtle and, honestly, the coolest. It's called induction. And here, you don't even have to touch anything. All you do is bring a charged object near a neutral one. So if you bring that negative balloon close to, say, a metal soda can, all the free-moving electrons inside that can are going to run for the hills. They flee to the far side of the can, leaving the side closest to the balloon with a net positive charge. And here is the really crucial part to get about induction. No electrons actually jump from the balloon to the can. None. The can is still totally neutral overall. All that happened is that its own charge got rearranged. It's a temporary separation, created just because something charged got close. So, we've got these charged objects, right? Now what? Why do they actually do anything? This brings us to the master rulebook, the one universal law that governs every single one of these interactions. It's called Coulomb's law. And don't worry, we're not going to get bogged down in the math. What's important is the concept. Think of it as a super simple set of rules that perfectly describes how charged things either push or pull on each other. Rule number 1 is the one everybody knows from school. It's just beautifully simple. Charges that are different, a positive and a negative, they pull toward each other. They attract. And charges that are the same, two positives or two negatives, they push each other away. They repel. Rule number 2 is just as easy to grasp. More charge means more force. So a balloon that has a huge buildup of electrons is going to pull on your hair a lot more strongly than a balloon you just barely rubbed. Makes sense, right? And rule number 3 is absolutely critical. Distance matters. A lot. The force doesn't just get a little weaker as things get farther apart. It gets weaker very, very quickly. Doubling the distance doesn't cut the force in half. It cuts it down to a quarter of what it was. So even a tiny gap can make that attraction or repulsion basically disappear. So what happens when you have a whole crowd of charges all pushing and pulling at once? You might think it gets super complicated,
But it's surprisingly simple. The total force on any one of those charges is just the sum of all the individual pushes and pulls from every single other charge. You just add them all up.
Okay, so we've got the rules of the game. Now let's use them in the real world. Why does your wool sweater get all staticky and clingy, but a metal pot in your kitchen doesn't? Well, it all comes down to what the material itself is actually made of. Materials pretty much fall into two big camps. First, you have conductors, like metals. In a conductor, electrons can roam around freely wherever they want. That's why that charge from your body spreads out instantly across a whole metal doorknob. But then you have insulators, things like plastic, rubber, or the air on a very dry day. In those, electrons are held super tightly to their atoms. The charge can build up, but it stays put. It's stuck. So wait a minute. If electrons are stuck in an insulator, how can it possibly be attracted to a charged object? The answer is this really neat trick called polarization. See, the electrons can't leave their home atoms, but the entire atom or molecule can sort of stretch and reorient itself. The negative side of the atom's electron cloud leans away from our charged balloon, which leaves the positive side of the atom just a tiny bit closer.
And that is the final piece of the puzzle. That's the secret of the balloon on the wall. The wall is a neutral insulator, but through this process of polarization, it creates just enough of a tiny, weak attractive force to overcome gravity and let that balloon stick right to it. It's not magic, it's just trillions upon trillions of molecules all doing a tiny little shift in response to the charge.
So that zap from the doorknob, it's you, rubbing electrons off the carpet, building up a charge that stays put because you're an insulator, and then that charge jumping through the air to the doorknob, which is a conductor. It's all governed by these same few simple rules. And this invisible force, it doesn't just explain a little shock or a party trick. It dictates the shape and behavior of molecules, which is the very foundation of all chemistry. Which really makes you wonder, what other profound parts of our world are being run by powerful forces we can't even see?